Hello, good evening. Welcome to Unacademy, which is the biggest online education platform for GATE, Computer Science and IT. Myself, Malesham Devasane. Here I'm going to start today the closure properties of recursive and recursively enumerable languages. Okay, this is the very important topic. Who wanted to learn undecidability? And you know that undecidability is one of the and you know that this is the very important topic for undecidability, where undecidability you want to understand, where you require to understand the closure properties of these two domains. So in these domains, complement operation is very important to understand the decidability and undecidability of the languages or problems. Okay guys, so let me begin. Yeah, Ishan, good evening. Akash, good evening. So I believe that you know the definition of recursive and recursively enumerable language definition. So even you do not know, I will explain that, then I will begin the closure properties. So before starting the today's session, let me talk about myself first. If you are attending the first time on this channel, myself Malesham Devasane, you can call me as Deva sir. I have completed MTech from IIT Bombay and also I have secured ordinary rank 119 and 210 in my BTech 4th year and 3rd year with self preparation, where I have so far 12 years of teaching experience almost, and I take TOC compiler programming on this channel. Okay, so this is my referral code DEVALIVE. DEVALIVE is my referral code. You can use it to get the 10% discount on Unacademy. You know that the price is going to increase on 28th October. So before that, please take the subscription if you are interested for plus courses on Unacademy. And you know there are various benefits of coming to Unacademy. You will have free classes, you also have a paid courses, but free classes are unstructured, but you will have almost every content you require from the subjects. I have taken CTOC compiler design algorithm so far, which have more than 300 hours so far. So you can go for GATE questions, new questions and mixed subject questions, and also regular courses, all the content available on free classes. And also you have a paid classes or paid courses on Unacademy. If you want to visit Unacademy, this is my URL, unacademy.com/DevaGateCSE. Please use this URL and click on follow me to get regular updates from me. And these are the benefits of press. One, you have live lectures, a live test and crash courses and doubt solving courses, and also rank improvement batches. Maybe you will have revision batches and also daily practice problems. So many courses are available on Plus. So that is the one benefit you have. And you have two kinds of subscriptions, Plus and Iconic. If you come to the Plus, I have told you that you have structured courses so that you will complete the subject in time without having the problem with dates. At Iconic, you will have all the benefits of Plus. Additionally, you will have a guide or coach to guide you all the time, and you will have a plan to prepare, and you will have guidelines to follow. These are the various benefits of Iconic. If you look at the price difference till 28th October, after that the prices are going to increase. Right now 22,500 for Plus for 1 year and 40,500 for Iconic 1 year. But use the code DEVALIVE to see this amount. After 10% of the discount, you have, including GST, you have the total amount that I mentioned here. Okay, but if you don't apply the code, the price is more than what I have shown here. And you can choose credit, debit or net banking, or even you can go for no cost EMI to complete the payment. And please join our Facebook group GATE Aspirants MECE CSE, and also we have Telegram channel to subscribe. Please subscribe to this channel to get regular updates and materials and notifications from us. Okay, these are the various free YouTube channels we have. Please share with your friends. If you have any friends they wanted to study from us, please share these YouTube channels from us. And if you are watching now, please like the session and also subscribe and also share with your friends. Yeah, let's begin the today class, guys. Okay, we have studied in the previous session Turing machines, that how to construct, what is the definition. Not much, but that is enough to understand the theoretical points of the recursive and recursively enumerable languages. Construction we have learned, and now we are going for the closure properties. Turing machine accepts REL, but we know we have also another machine, halting Turing machine. This is also Turing machine, but a special Turing machine which accepts recursive language. But before starting today's session, guys, I want you to understand what is recursive and what is recursively enumerable. Everyone, guys, come on. Respond, guys. Today's session I am talking about, if you want to understand undecidability, this chapter is the beginning. This topic is the beginning for undecidability. Okay? Yeah, let me talk about first what is a recursive language. What is recursive language? Why we are talking about closure properties of recursive languages? Here we have infinite recursive languages, but every recursive language is accepted or acceptable by a Turing machine that always halts. But also remember, guys, you can design a Turing machine even though it may not halt all the time, right? You can design a Turing machine that halts for even valid strings only. Remember that too. Yes, always, not every Turing machine, guys, we have existence of STM. Remember that. There exists TM that halts always. Don't say that every TM that accepts recursive is halts. That's wrong. There exists TM that always halts. That halts always. Everyone, guys? Their existence we are talking about. Also, we have Turing machines, whether they halt or not. Remember that too. Okay, that is the recursive language. And these 2 points are same, guys. Now I'm talking about, we will have a Turing machine. We can have a Turing machine that can enumerate lexicographically. If you want just enumerate, you can, but you can also enumerate lexicographically. That's about recursive language. Yeah, good evening, Ganship. Good evening, Hiran. Sai Prakash, good evening. Yeah. This is about recursive language. Now, what is recursively enumerable language? Lexicographical means we talk about effective order. Recursively enumerable language, you can simply call RE language, REL. So what is REL? We will simply say acceptable by TM. Whether it halts or not, we really don't know. It may halt always or it may not. Depends on the problem, depends on the language. And we also know enumerable by. The language is enumerable by TM. Is it effective or not? We really don't know. Yeah, Gunship. Okay, I got the point. You are the Turing machine. Great. Everybody clear about this? And whenever somebody talking about recursive language, it's like halting program. It's like halting program. We have halting program, like we have algorithm. Simply, algorithm exists. When we are talking about a recursively enumerable language, we can say program. We don't know whether algorithm exists or not. Algorithm may or may not exist, guys. Program exists. So recursive languages are like algorithms. We have an algorithm to understand recursive languages, and recursively enumerable languages, we have programs, but we don't know whether we have algorithm or not. Yes. Yes, we have so many names. Recursive language also called as a decidable language, and recursively enumerable called as semi-decidable. Semi-decidable. We have so many names for this too. We have seen in the previous classes already. Guys, anybody who was not there in the previous classes, please go and watch previous classes. I have told you the synonyms of this too. I'll come back to synonyms after today. Tomorrow, I'll come back to them again. But today, I'm going to talk about the closure properties. And what are the closure properties we are going to learn today, guys? Mainly union and intersection and then complement. These three are very important to understand with proofs, but after that you may remember them if you want, whether they closed or not. And so far the complement is very, very important to begin the undecipherability chapter. Okay. Fourth one. What is NPP? It doesn't matter, NPRP. Algorithm exists, whether it is polynomial or non-polynomial, doesn't matter. Fine. Now let's look at, guys, remaining like, a reversal, operation, concatenation, and then difference. Okay, so let me give the space here. Seventh, clinic closure, like clinic star, clinic plus, and you may have subset, substitution, f of L and h of L, homomorphism, guys, epsilon free h of L, epsilon free homomorphism, inverse homomorphism, and so on, coefficient, all of them, right? So these are the very important operations, guys. These are the very important operations to remember. And just I'm making the table before starting these three operations, guys. Okay, first column is about for. Recursive languages. For recursives, let's say, for RELs. Similarly here, recursive languages and RELs. Okay, what is important here? As I said, complement. So far, this is important. Complement is closed for recursive languages, not closed for RELs. Not closed. So even I'm going to repeat. Why closed, what is closed, what is not closed also, guys. Intersection, if you look at intersection, closed, these all are closed, guys. Reversal, concatenation, difference when it comes, this is not closed. Look at that, because of complement, guys, because of complement. And clinic closure, all of them are, guys, so far everything is closed. Subset, they are not closed for all the domains that we have studied so far. And F, when it comes, it is not closed here, but remaining all are closed. So these are the important operations. Wherever I have marked not closed, that is most important for the exam point of view. Everyone, guys, complement is not closed for RELs, so difference, and subset is not closed for anybody. And we know F and H are not closed for recursive languages. When I am going to talk about recursive, guys, you can remember them simply, because proofs are really difficult at undergraduate level. So I can tell you something for recursive languages. Recursive languages, what do you remember? You just remember which are not closed. That F, H, and subset anyhow is not closed. These are the important three operations from this table are not closed. And when it comes to RELs, what do you remember, guys? Complement, difference, subset anyhow not closed for entire domains that we have studied so far. Yeah. So is that clear so far? The remembering the table is not difficult, but understanding the table really difficult for you, because you need to remember the proofs, you need to understand the proofs. Okay, so I'm going to explain the proofs for the first three operations: union, intersection and complement. Remaining, obviously it may take time to understand, but we are not much worried about others. Clear? Good evening, Deepika. Everybody guys? Okay. And to understand this, let's start what is closed and not closed, because we have two domains guys here, recursive languages, and that means we must have a domain first. You can take any domain, you can take regulars, you can take non-regulars, anything, doesn't matter, but first fix the domain. Fix the domain. This is our domain. That's domain, really it's your choice. Domain may be set of regulars or set of non-regulars. You take anything, I don't care. First you fix the domain, set of that recursive languages or set of RELs, so many are there, etc. First fix your domain, right? So that I can talk about the operation. Then operation, we will fix an operation to talk about. Of course you can take any operation. Operation is maybe union or intersection or complement or difference or anything like that, right? We have two things when we are talking about closed or not closed. If you want to say closed, very simple guys. If you want to say closed, let's say I have infinite elements here, infinite languages like L1, L2, L3, L4, L5, L6. There are infinite languages here. If it is closed, what is the definition guys? If it is closed, take any Li, take any Lj. If any operation is closed, that for all Li, for all Lj belongs to that domain, the result Li star Lj belongs to same domain. Right? So why we are not good at understanding the closure properties? Because we are not actually looking at what we want. Our domain is fixed. If I say, is this union, let's say something like that, reversal, is it closed for non-regulars? If you take any non-regular, if you do the reversal, you should get non-regular, because reversal of a regular is regular. If one of them is regular, other is regular. So reversal of non-regular is always non-regular. So reversal operation is closed for non-regulars guys. Also reversal is closed for regulars. So it is important what is you are going to take as an input, and also what will you get an output. If the input and output from the same domain always, then that operation is closed. But it is given that input and we are looking at what is an output. Everybody guys? So it's always given input and we are observing is that output belongs to same domain or not. So that's about closed. This is about closed. The star is closed, if you want to say. But I want to say star is not closed guys. Star, I want to say not closed. Star is not closed. Then how do you say? Now we will not look at entire domain. You need to take at least one example. There exists Li, there exists Lj, but its operation when we apply it, I'm talking about binary, it may be unary sometimes. Okay, Li star Lj not belongs to same domain. Means it goes outside the domain basically. Right? Everyone guys, this is the most important point. How do you look at any point that I discussed so far? Okay, let's start the closure property guys. Let's start the closure properties one by one. So first I am talking about union for recursive languages. What is the meaning of that guys? I take one recursive, let's say any recursive. Here also I take any recursive. But I'm assuming this is L1, this is L2. L1, L2 same or different, doesn't matter. Then when I apply union, The result is L1 union L2 is always recursive. Then only I can say union is closed. That means recursive language union, recursive language is always this side only, guys, one direction only. Result is always recursive. Everyone, guys, we have a domain, we pick any two recursive languages, we do the union, we will get a recursive language. Then what will be the proof? Yes, we require, and also good point here. So whenever we have a closed, we may require a proof as algorithm. Proof is algorithm. Whenever it is not closed, the proof is an example. Proof requires an example to show that there exists input but output is outside the domain. There exists an input from the domain but output is outside the domain as per the closed not closed definition. Yeah, this is the counter example. You can say that. Okay, let's move. Now this is the closed. We say that union is closed for recursive languages. I can say for set of all recursive languages. We just don't say one recursive, guys. We say set of all recursive languages. Okay, or I can say set of all recursive languages is closed under union operation. Okay, now let's look at the proof. What is the proof? We know recursive union recursive is recursive. I'm trying to give a proof, guys. So assume this is the L1, this is L2. I'm trying to show L1 union L2 is recursive. If it is L1, can you build halting Turing motion? You know the concept. Note, what is the concept I'm following? Every recursive language definitely has, every recursive language has halting Turing motion that accepts given L. Everybody? Even also I will have non-halting Turing motion, that's okay. Yeah, Aditya, I really don't know. I will come back to that notification in coming classes. Okay, every recursive language has HTM, IC, RB notification. Okay. Now, because of this reason, I can design HTM1 for L1. I can design, of course, we can design HTM2 for L2. So I'm doing that. Guys, this is HTM1. This is HTM2. Right, let's take some string. And guys, you know, if W belongs to L1, it halts always. W not belongs to L1, even though that not belongs to it halts always. Both the sides it halts. Why? Because it is halting Turing motion. The nature of the halting Turing motion is always halts. And I have halting Turing motion for L1, halting Turing motion for L2. So this is everybody knows in the world. But how do I know that? How can I prove that, guys? How can I prove that I will have halting Turing motion? I will have halting Turing motion for, if there is halting Turing motion, I must prove something. I don't know really I have or not. I'm trying to check, guys. I'm trying to check. If I have a halting Turing motion, L1 union L2, if the string accepted by any halting Turing motion, then we must show I can halt. And W not in L1 union L2, I must show I will halt. And I will give a W to this new motion. So I'm trying to show, will I have HTM for L1 union L2. I'm trying to design that. I'm trying to check, do I have halting Turing motion for the union? So if I have, tell me guys, we always halt here. As per the definition, this halts means logic exists. This halts logic exists. Logic exists for belongs to, not belongs to of every motion of the language, right? But if it is belongs to L1 union L2, what is the meaning of that? You give this W to both the machines, both the halting programs you can give, and just you need to cross check. You need to cross check. If any of the, just like R, OR, if any one of the machine halts at final, then you halt at final. So what is the logic? If any HTM halts at final, then new machine also halts. Is it clear? Any means R here. That means we have a logic. We have a logic to halt at final. I'm showing how you can halt at new machine that is also at final. Now, how do you show that union invalid strings? Now, I'm trying to show that these are invalid strings, guys. Take the logic of not belongs to L1, and if both, this is going to be both, guys. This is and. If both machines halt, if both HTMs halt at non-final, then new machine halts at non-final. That means I'm clearly showing that I will have HTM for L1 union L2. That is the reason you have union is closed for recursive languages. I will take two halting programs. I can combine the properties of two programs to make another new halting program, right? To have the property of the two languages. Yes. Anyhow, that union intersection is not much difficult, guys. This is without any example, you can prove this. You can ask any problem in the world which is already a recursive problem. I can combine with another recursive problem to get a new recursive problem. Okay. Just like, I'm just giving an example, guys. Just example, not required, I'm giving it. I'm just taking about a language. Set of, x such that x is even. Let's say L1, L2, x such that x is prime. Guys, these two languages in the world, they are recursive. This is a set of even numbers, even natural numbers, and this set of prime numbers. So now if I do the union, L1 union L2, definitely this is the recursive. L1 is a recursive, and that we will know slowly why it is recursive. But if you can understand the problems, now I am trying to show that x such that x is even or prime, that is also recursive. How can you show that? You can write a halting program for L1, halting program for L2. Then you can call the two halting programs. You can observe the properties of two programs to decide the answer of the union. This is how real-time example for the recursive languages. Recursive languages, guys. Set of even numbers and set of prime numbers, both are recursive languages in the world. Okay, that you can take two regular languages, or one regular, one CFL you can take, or one context-free language, one deterministic CFL you can take. Anything, doesn't matter, but take two recursive languages. Everybody, guys, it is interesting real-time example to understand recursive union. Recursive is always recursive, right? Recursive union, recursive is always recursive, guys. There is no doubt about it. In the exam, you may get so many questions for this, so many. I'm just talking about finite union recursive set is dash, or regular union recursive set is dash, and DCFL union recursive is dash, and CFL union recursive is dash, and CSL union recursive is dash. and recursive union, recursive is dash. All of them blindly is recursive. Because others also you can consider as recursive. No doubt. But intersection, be careful. Certain properties will not help you. Are you clear? This is the interesting gate question possible, or any competitive exam they may ask such questions. Okay, so such questions I may ask many too, like finite set union regular set is, can I say recursive? Yes, I can say recursive because it is already regular. So I can say DCFL, I can say CFL, I can say CSL, I can say recursive because it is one direction. Even I can say recursively enumerable language. Everybody guys, look at that, how many answers are there, because this is given to you, this is given, and we need to find what it is, right? But if regular is given, I can't guarantee it is a finite union regular. There could be multiple answers. If the result is regular, input can be anything. But if input is given, answer can be understood this way. This is a very interesting property of, okay, finite union regular. All the answers are right. Multiple choice MSQs possible from here. Everyone, okay, let's move to REL guys. Let's move to union of two RELs. That means REL1 union REL2. I have to prove that always REL. I have to prove that always REL because union is closed for set of RELs. Union is closed for the domain of RELs. That means you take any REL, any REL, doesn't matter. I have to show that after performing the union, result is also, like let's say L1, L2. L1 union L2 is always REL. We don't know whether it is regular or finite or recursive because RELs can be even, I can take two finite languages, finite union finite, maybe finite, but that is always REL. Remember that. So here so many interesting questions comes out now. I have to prove that by taking two RELs, the result is always REL. So far there is no connection with undecidability, but in future you may be asked the relation with decidability, undecidability. Here guys, why I am saying this is going to be beginning of decidable, because when I am talking about recursives, decidable language, union decidable language, you have to say it is decidable language because recursive language, another name is the decidable language. Everybody guys, this is the most important factor why we have already started decidable chapter. Decidability and decidability is already started, but people have to realize, you have to realize the recursive language, another name is decidable. Okay, let's look at now how can I prove that REL union REL is always REL. Let's move on to proof guys. I want to prove REL1, just one REL guys, one REL union one REL. I have to prove it is always REL, one direction only. So you know that concept of this, if it is REL, what is it? Every REL as Turing motion. But guys, it may have a finite automata, it may have a PDA, it may have ordinary motion, we don't know. But definitely you have a Turing motion. Whether we have or not other motions, but we will definitely have a Turing motion. So using this fact, we can construct TM1 and TM2 for REL1 and 2 respectively. Everyone, so I'm assuming that you already have the Turing motion. You already have a Turing motion for REL1, for REL2. We have, I'm assuming it because that is given to you. So what it does basically, what is the Turing motion definition, guys? What is the Turing motion definition? You must follow definition now. I'm assuming this TM1 accepts REL1, TM2 accepts REL2. If really accepts, we have a definitely logic for all W belongs to REL1, it holds definitely. But W not in REL1, we don't know. Don't say we don't have a logic. We don't know. If it is always halting, we will have a logic. If it is not always halting, we may not have a logic. Right? So that is the important factor of the Turing motion definition. But not belongs to, we are not having a clarity because we don't know which Turing motion we are talking about. We don't know. That's the best word we can use for the Turing motion. Because in general, I want to talk about any REL. That may be regular, that may be DCFL, that may be recursive, even that may be not recursive, but it is REL. But all of them, this definition satisfies. We don't know for invalid strings. We may have a logic, we may not have a logic. Now, can you show me? I want to think about, is there any Turing motion? If there exists a Turing motion, you must build a logic for W belongs to union and W not belongs to union, no need to build a logic. So now we have to show that. Okay, W I am giving to this motion, new motion. Why? Because I am trying to show Turing motion for REL1 union REL2. I am building a motion for union. Then I have to show that W belongs to REL1 union REL2. You must show I will halt always. And if not belongs to, for every string I am talking about, REL1 union REL2. No need to show that. No need to show anything. Because we don't require a logic for not belongs to. So now, what is the logic? Guys? What is the logic? What we do, if this motion all set final, then what we do? If any one of them all set final, this is our logic. If any one of them all set final, if any Turing motion, again same like the previous HTM, if any TM all set final, then new TM, that is we are designing for union, new TM also all set final. But other side, we don't require logic. You can just ignore them. Everybody, guys, this is what a Turing motion definition, and we are following Turing motion definition to prove it. The previous example will work here. The previous example, guys, you can use this example. Set of even numbers, set of prime numbers, both are REL already. The result is again REL. You can show the logic for just valid strings. Invalid strings, no need to show the logic. The same example will work because already they are recursive languages. Let's come to the point. So do I have a Turing motion for the union of two RELs? Yes, we have, always. Now let's look at examples. Now guys, I know REL1 union REL2 is always REL. But if somebody asking about finite, may or may not be finite. Or may or may not be regular. It could be anything. We don't know about regular also. Or may not. Don't say not. May or may not DCFL, or may or may not CFL, may or may not CSL, and may or may not recursive, but always REL. REL union REL is always recursively enumerable. Come on, guys. REL1 union REL2 is always REL. Now using this fact, now I can ask some questions like, finite language union REL is, can I say REL? Obviously I can say it, right? Because REL I have a Turing machine, finite set also I have a Turing machine, I can build a new Turing machine for union, right? I can say regular set union RE or REL, both are same for me guys, is also RE. And DCFL union REL is REL, no doubt about it. And CFL union REL is definitely REL. And CSL union REL is REL. Recursive union REL is also REL. Everyone? Because REL is the most powerful program than compared to other operands for the union. Okay, this is the most interesting property of the union, guys. Yes, you can easily understand union, but intersection you need to be careful because of the finite language. Intersection with anything is a finite. So except that remaining all are fine. Okay, there I am not going to talk about the finite. So are you ready for intersection, guys? Are you ready for intersection? So using this logic, you can show that. I'm directly saying that, I'm trying to prove directly, guys. Now this HTM1 exists definitely for recursive one. Okay, W belongs to, let's say L1 or, okay, recursive one. And W not belongs to recursive one. Both side logic exists because of it is halting Turing machine. Here also HTM exists. TM also exists, guys. Remember that. Even though it is not HTM, TM also exists. Don't take that. HTM exists for recursive language 2. And W belongs to recursive 2. Logic exists. And not belongs to also logic exists. So now I can build a new HTM by taking the consideration of these two machines. Okay, now I can show that W is given to both machines, and I can show that W belongs to L1 intersection L2. I can show the logic. Not belongs to L1 intersection L2. I will show the logic. What is the logic, guys? Now this time, if both machines halts at final, then only new machine halts at final. And we have to do now, what is that? If it's not a digital logic gate, guys, it's a program. If both HTMs halts at final, then new machine halts at final. The new HTM halts at final state. Now what is the logic for invalid string, guys? You can use R now. You can use R. This is R logic. If any HTM are set non-final, that means that string is not there in the both. If any HTM are set non-final, then new HTM that we are designing now halts at non-final. So we can write a halting program to understand the new problem, that is intersection of. So we have, I can say now, we have HTM exist for recursive 1 intersection recursive 2. We have proved it. Clear this point, guys? And we are just beginning. This our results are going to be very important for coming classes, guys. Okay, recursively is clear. Now I'm going for directly intersection of RE languages. Same. Okay, W. I'm saying that intersection now. TM for L1. Assume L1 is REL. And just think about W belongs to L1. Don't worry about W not belongs to L1. Really, we don't know. Put a question mark. Put a question mark because we don't know. Tm for L2. L2 is another REL. REL intersection REL, I am proving it. So W belongs to L2. We will have a logic. But not belongs to L2. Really we don't know. So now we have to build a new Turing machine. If it exists we will build, otherwise we can't. I want to show that I will have a logic. I will have a logic. W I will give to both machines. If really W belongs to intersection, I must show a logic. Show logic here. And W not belongs to intersection, no need to show anything because it is a Turing machine. No need to show any logic. Why? Because Turing machine will not talk about invalid strings of a language if really not exist any logic. Okay. Now if a logic exists for belongs to same logic and logic, if any TM alls at final, then new TM alls at final, right? And logic guys, and now here we no need to prove that what is not belongs to. So that means now I have proved it. TM exists for intersection of L1 and L2. That means REL1 intersection REL2 is also REL. REL1 intersection REL2 is always REL. So I have proved it. Hence I have proved it. I have an REL for intersection. So I have a Turing machine for intersection of two RELs. Okay, now we will move to the interesting property. This is where the undesirability chapter begins, guys. So far I don't know how will you utilize the properties, but now onwards it is required to understand each and every word that I speak. Now complement is closed. The complement operation is closed for recursive languages, or you can say set of recursive languages. It means you take any REL, do the complement, it is again always REL. Always what is that? REC, right? Sorry. You take any recursive, again it is always recursive. Okay, because recursive languages are closed under complement. Recursive languages are closed under complement. What is the meaning of that? Suppose I have a Turing machine, alternating Turing machine. I have alternating Turing machine, let's say for L, where L is the recursive language. It means W belongs to L, W not in L, both side logic exists. That is the meaning. Logic exists for both valid strings and invalid strings. Now somebody has to prove that I also have. Somebody has to prove that I also have alternating Turing machine for the complement of L. What is given? That is alternating Turing machine of L only given. Now I want to prove that W belongs to L complement, W not belongs to L complement. Then I have to prove that I have a logic. Prove or show logic exists. You have to show, guys. Show logic exists. You have to show even here also, because the alternating Turing machine. Now I am trying to prove that HTM exists for L complement. I am trying to prove that. I am prove HTM exists for L complement. How do you prove? If W not in L, the same logic you give to this one. If because W not in L means W inside L complement. If W inside L, then give the logic to W outside L complement. And that's all. If alternating Turing machine exists for L, indirectly complement also alternating Turing machine exists. Then if you want to understand this with a real-time example, it is important. Just you can try that. I have L is equal to, that I said X is even. That means it's set of even numbers. set of even numbers. Now you have designed HTM. You have designed HTM to accept L. That means when you give a number, if W belongs to L, it says even. W not belongs to says, it says odd, right? So definitely we have a logic, some logic to find out even, right? To find out even, we have a logic. If it is even, that is belongs to. If it is not even, that is not belongs to. Now, can you show that the complement of L, guys? What is the complement of L? That means X such that X is not even. Indirectly, set of not even numbers. Not even numbers means set of odd numbers only. Then how do you prove that logic, guys? You have to prove using Turing motion, halting Turing motion. Can you show me halting Turing motion for this? Everyone, guys, using the existing only, no need to build again. So what I am going to prove now, I will give a W to the same motion. If this says odd, now I am trying to build HTM for L complement. L complement means is X not even. Not even means this one. If W belongs to L complement, and we'll take this logic, the W not belongs to L complement. That means X is not even, and not of not even means X is even. Everybody? Come on. So I'm trying to give an example to understand the proof. Okay, so very interesting question, guys. Let me take that. All HTMs accept some recursive, or some HTM don't accept recursive. Random stuff. If you say HTM that should accept recursive, there is no HTM that doesn't accept recursive. ये क्या यार? HTM equivalent to recursive set, because language accepted by HTM is recursive set. What is important? Every recursive set has equivalent infinite HTMs you can design, but every HTM it accepts one recursive language only. Every HTM accept one recursive language. ये तो करना पड़ेगा ना आपको. Come on. If I have a recursive set, I can design infinite equivalent HTMs, no doubt. But if I have HTM that accepts only one recursive language, because HTM is for one particular application. Clear? Random stuff. Every HTM has to do recursive. If you collect all the HTMs in the world, you will get all the recursive. If anybody says, guys, set of all HTMs, set of all languages accepted by all HTMs, when we collect them, you will get set of all recursive languages. No doubt about it. You will never leave any recursive language. If you collect every HTM in the world, you will get every recursive too. But if I have a recursive, you no need to design HTM. You can design even Turing motion, which is not HTM. Right? I'm telling you again, guys, recursive language, two options. HTM exists, indirectly Turing motion exists, even non-HTM also exists. But that is Turing motion, TM exists. And this is already TM. Understand, recursive language definitely HTM exists, but no need to design HTM if you don't want. I can say every recursive language, there is equivalent HTM somewhere in the world. Every recursive language has equivalent HTM, but I am not saying only HTM exists, equivalent HTM. Right? but also every recursive language has equivalent Turing motion. Also you have equivalent Turing motion, whether it is HTM or not. But Turing motion, no need to do recursive. The one direction, guys, one direction. Every recursive language I am talking about. So understand these words plays very important role when you are talking about. Okay, when I am talking about REL, I can't say no alternate Turing motion. Always, okay, what always I can't say. I am saying Turing motion exists. TM exists. TM exists. But you may have finite automata if you want. If it is already a regular language, or you may have DPDA. I don't know. You may underline it. You may have HTM. That's okay. But I am talking about Turing motion. Definitely Turing motion exists somewhere. That doesn't mean that finite automata doesn't exist. It may or may not. Depends on REL. Yes. If there is no HTM, then we don't know. It may be, guys, good point. If there is no HTM, for L, then L may be REL, or depends on the problem. L may be not REL because that depends on L. That depends on L. If L is not REL, definitely no HTM. Even L is inside REL, but which is not recursive. REL but not recursive. L may be REL still. Okay, come to the point, guys. Doubts later. Now come to the point. Complement of RE. We know REL complement is, we don't know. Maybe it is REL, may not be. Why guys? When we build a Turing motion for any L, what is the reason is W belongs to L, we have a logic exist. For all W we have a logic exist. But here W not in L, we don't know. This is a very interesting point, guys. W not in L, we don't know. Logic exists or not, we don't know about logic. It may exist, it may not. Then if you want to do the complement, guys, definitely you can't get desired one. Why? Because you have to show W belongs to L complement. Okay, it looks like I should go down. Okay, I have to show W belongs to L complement. We should show logic exists. And W not in L complement, no need to do anything, no need to show. But we know that logic doesn't exist. We can't prove it. We can't show that. The reason is this is the connection. Already we don't know about logic. We don't know, guys. Yeah, there is a problem with the slide. Okay, we don't know about belongs to of L complement. That is the reason we can't guarantee REL complement, is it REL or not. To understand this, I want you to focus on this. Whatever I discuss in the next few minutes, focus on this one, guys. Focus on this one. So what is the conclusion, guys? We can't prove TM always exists. Sometimes exists, no doubt, for L complement. Sometimes may exist for L complement, but sometimes no. That depends on whether you have a logic for, that depends on invalid strings of L. Depends on invalid strings. Depends on here. Everyone, come on. Next point. I want you to focus on the next slide that is very important for you. That is undecidability is going to begin slowly from here. As we know, here all recursive languages, not one guys, infinite recursive languages are there in the first box. First box we have infinite recursive languages. But the second one, that all RELs, all RE languages, including recursive languages guys. But this is very special class. This is a very special. They are all RELs but not recursive. All RELs. RELs but not recursive languages. Everyone, now look at the point here. If I take the language which is inside this one, its complement is here inside this box only, because recursive complement is always recursive. Recursive set complement is recursive. No doubt. That means I can say that L1 complement is recursive. If L1 is recursive, then L1 complement is also recursive, because L1 is inside the recursive class. Now, if I take this language guys, L2, that you can't say RE, simply REL. You can say that RE but not recursive. That complement is definitely not REL. Why guys? Which directly goes outside. This is not REL. Outside the REL class. Why is that? Because that machine clearly guys, the invalid string will never have a logic. Even we don't know, we will not get that. We will definitely get no logic for invalid strings. Why is that? If you have a logic, that must be recursive. So somebody might talk about now, what is REL complement? It means either you might be talking about L1 complement, or you might be talking about L2 complement. If it is L1 complement, that could have been recursive already. Or if you are talking about L2 complement, that is already not REL. So the interesting answer guys, very interesting answer. Anybody saying RE complement is, we know, need not be REL. But we are sure now is either recursive or not REL only. The reason behind it, can you see that within REL, if when you take any language, nobody coming to RE but not recursive. These languages, recursive languages, are inside recursive after complement, and REL but not recursive after complement, they go directly outside REL. So it means nobody comes to the REL which is outside recursive. Okay, this is what the decidability and undecidability definitions begins. And if you are not clear about this, I can say that REL complement never be REL but not recursive. Remember that. Never be. You can't prove that any complement of REL is inside, that never comes to this position guys. This position I am talking about, this position is very interesting guys. This is REL but not recursive, right? In this class, you can look at that. Complement of any REL will never come to that box. Okay, so tomorrow I am going to continue from here. Tomorrow guys, I am going to importance of complement and important points. Then today we have learned union, intersection and complement, and these two are closed for both domains, closed for recursive languages and RE languages, even this intersection also, but this is closed for recursive languages but not closed for. Tomorrow I am going to begin from that complement, and that is the beginning of undecidability chapter. Okay, this is today summary guys. Union, intersection closed for both the domains, but complement is only closed for the domain of recursive languages, not closed for domain of RELs, because sometimes REL complement can be REL, sometimes REL complement is not REL. So that is the reason REL complement need not be REL. Okay. Okay, random stuff. Good question. Anybody says, guys, if REL complement is recursive, then REL has to be recursive. Very simple. REL must be recursive. This REL must be recursive. The reason is recursive complements only recursive. Recursive complement only recursive. If you say not REL, not REL complement never be recursive. Guys, anybody saying if L complement is recursive, it means L has to be recursive. Not only this, guys, if L is recursive, then L complement is also recursive. 2. L is recursive if and only if L complement is recursive. Remember this point. And this is what tomorrow begins, guys. Don't worry much about this. Okay, so anyhow, I'm going to stop today. Tomorrow I'm going to talk about important points. Come up with the doubts if you have any and post in the chat. I will take up before taking the class, but have doubts before starting the next session. Thank you so much. And this is my URL to follow my classes, and visit devagatecse.com to see all the links of Unacademy special classes, and please follow all the classes of our educators. We are trying to teach you which requires for your preparation. And thank you so much, and like this session, and we'll meet in the next session. If you are not subscribed, please do that, and also share with your friends. And if you are enjoying, please don't forget to like this session. Thank you so much. Bye bye.